Hi guys, this video is supposed to help you with analysis for task 2 for our third lab, which is called the vector lab, where you deal with the force table. So just as a reminder, this is the task 2 that you're supposed to be doing, right? We're setting one of the forces on a force table with a lot of mass at any angle that's not exactly at the axes. So not at 0, 90, 180, or 270. And we're trying to find the two perpendicular forces, one being horizontal and one being vertical, that create equilibrium. And this video is going to mostly focus on the percent error of it, how to calculate percent error. We sort of talked about this in class, but I just want to put a video out to make sure everyone's on the same page. So to understand this, let's have like a sort of small diagram, right? This is a aerial view of your force table. Obviously, without all the angles listed, it's just the four right-angled ones. Let's say for my choice, and your data is gonna be different, right? Let's say I choose to put my single force that I get to choose at 140 degrees, which looks somewhere like this, right? My arrowhead's like that, and this whole angle here is 140 degrees. Actually, I'm gonna type it out. 140 degrees, right? So if this whole angle is 140, we want to try to see what two perpendicular forces can cancel this one out. So if we think about it, this one force here, 140 degrees, pulls the center ring up and to the left. So to combat that, we need to have our other two forces, our two perpendicular forces, to the right and downwards. Right? Our two extra ones need to be to the right and also downwards. A certain amount to cancel this one out. Right? And that's our goal of the experiment. So let's say our data that we found over here. We put our force mass, original mass, as 400 grams, like I said earlier. I put 400 grams at 140 degrees. So this magnitude is supposed to be 400 grams, but we're going to label it with a force. To find how much weight it is, you first convert it to kilograms, which is divided by 1,000, and then multiply by, equals this guy, not that guy, times 9.81, and this is the weight, right? Is about 3.924 newtons. Now, for this one, you're not doing a scale diagram or anything like that. This is just a diagram to show you what's going on, to visually see it. So, and we said we put this one at 140 degrees. I'm going to type it over here at 140. And in a previous video, I mentioned how Google Sheets doesn't work with the degrees. It's going to work with radians instead. So to change it is equals radians, parentheses, and I click on that angle. So now 2.44 radians is the same as 140 degrees. And so after I put this fx, which is going to be in the 0, I can type over here at 0 degrees, right? Because this horizontal, to cancel it out, is going to be at 0 degrees. And this one, the vertical one, fy, is going to be at 270 degrees. So I'll type over here at 270 degrees. Let's say, based on my experiment, I've moved the numbers around. I found that 300 grams added onto here makes it work, and 260 grams here makes it work. All right, now this is including the mass of the mass hanger, so really this is 200 grams in addition to the mass hanger, because the mass hanger is 100 grams, and this is 160 grams in addition to the mass hanger. So same calculations, we need to convert to kilograms, so I'm just drag this down so it does the same calculations, and same as the weight. And the direction here, I already tucked it in here, but just to reiterate it, 0 and 270, and I want to find the radians of those, so same thing. These values here are not completely necessary here, but it's nice to list it out anyways. So this is all the experimental data, right? Based on my data, this stuff, one force at 100, at 140 degrees with 400 grams on it, balances out with a horizontal one at 0 degrees of 300 grams and a vertical one downwards at 270 degrees with 260 grams, right? So this is all our experimental data. Let's understand what this means, or how to think about this. if we have this one single force here, right? So let me just backtrack here. How do I? Oop. Okay. This total one at 140 degrees, right? We've learned in class how to break this up into its components. So let's type it over here, 140 degrees again. We've learned how to break this into components, right? Because this is a diagonal. It's not completely vertical. It's also not completely horizontal. So to combat that, or to simplify, to understand it easier, we can think of, instead of this one diagonal force, we can think of it as two horizontal forces, right? I mean, two perpendicular forces. One, and I want to change a different color. One this way, one horizontal, and also another one vertical. These two added together is the same exact thing as this one diagonal one at 140 degrees. I'm trying to make this one thicker. Yeah, it's easy to see there. So these two perpendicular ones, this one horizontal, this one vertical, make up this one. That's what a component is, right? These two are the pieces to make up this whole. So if you want to calculate how much that is, we've learned these equations in class where for any vector a sub x is equal to a times cosine of theta. And a sub y, the y component, is equal to a times sine of theta. Right? Where theta must be the angle of the vector measured from the positive x direction, right? Which this 140 degrees is, right? This is the positive x direction to the right, and so it's measured counterclockwise to that. This vector here, just diagonal, is 140 degrees counterclockwise from the positive x direction. So for this example, our theta is 140 degrees. So if we want to figure out how much of this, and this we calculated earlier, was a force of 3.924 newtons, right? This diagonal is 3.924. If we want to figure out how much of this is horizontal, we can use this a sub x equation, right? So if we do it in, a sub x is equal to 3.924 times cosine of 140 degrees. And the same way, a sub y is equal to 3.924 times sine of 140 degrees. So if we think about this diagonal force, right, it's, instead of thinking about this diagonal force, we can replace it with ideas of this one horizontal to the left and this one vertical up, right? So how do we combat these? How do we balance these out? We balance it out by having an additional force, whatever value a sub x is, a sub x amounts of force to the right to combat the one on the left, and a sub y amount of force downwards to combat the one going up. And that's exactly what we're doing for our lab, right? We're figuring out, we're trying to add enough weight so we get a sub x here and get a sub y there. So those are our ideal values. Those are our accepted values, how the numerical solution of it. So if you go to a sub x accepted values, for f of x, the horizontal magnitude, it would be a sub x. So in this case, it's equal to this weight times cosine of, and remember, our angles are always in radians, so we're using this angle in radians. Right? Now, why do we get a negative number? The reason why we get a negative here is because this is the x component of this, which is in a negative x direction. For our purpose, we're going to ignore negative signs, right? So I'm actually going to change this in the beginning here. If you look where my mouse is, I'm going to make this absolute value. ABS, open parentheses, I'm going to close parentheses all the way at the end. So now it becomes a positive. Okay, I'm going to continue this on the next video.